What is the bioenergetic perspective on the lean mass hyperresponder hypothesis? In this video, I want to go through the lean mass hyperresponder hypothesis. I want to discuss the importance of energy metabolism in this hypothesis, talk about the difference between the lean mass hyperresponder hypothesis and actual atherogenic dyslipidemia, talk about the centrality of energy failure as the key here, and also talk about why this doesn't necessarily mean that we want to go on a high-fat diet. Now, this video that I'm creating here is not to bash the lean mass hyperresponder hypothesis. I actually think it's a great hypothesis. I respect Dave Feldman and I think it's Nick Norwitz for the work that they've done to actually take the time and energy and effort to flesh out this hypothesis, understand the mechanisms, test it out in humans, and start to understand what's going on. Now, my goal is to actually participate in this discussion and the overall picture, and not to make this a anti-low carb or pro-high carb debate. I actually am interested in this in terms of the mechanisms and understanding what's going on in this lean mass hyperresponder hypothesis and how this is actually extremely useful for understanding cholesterol metabolism as a whole and how it actually tacitly picks out and destroys the lipid hypothesis to some extent. So in this video, what we're going to do is we're going to cover the actual value of this model first. So why is it even important to look at? What is the relevance? Then we're going to talk about the model. I'm going to go through it, go through the paper that Dave Feldman and his team have actually put together to describe the mechanisms. I'm going to talk about the importance of energy metabolism being central here. I'm going to dive into the differences between the two lipid profiles, and then we'll talk about why this doesn't necessarily mean that high fat is a good idea. So to start, what is the value and the importance of the lean mass hyperresponder model? Well, the first thing is that it starts to put cholesterol into context. So it's instead of this idea that cholesterol is just bad and that we just need to lower it by all costs, the question starts to become, why is cholesterol elevated in the first place? Now, many people in the low carb sphere, many people in the bioenergetic, the paleo spheres have been asking this question about cholesterol and heart disease for years at this point. And now we actually have another hypothesis, another arrow in the quiver to start to say, okay, maybe cholesterol is elevated for particular reasons. And rather than just focus on cholesterol, let's focus on the underlying problem that's causing it to be elevated. And also, is it being elevated always a problem? Or is there something else going on? So this hypothesis is another way or another door to understanding the different contexts in which cholesterol is elevated. And some of the contexts that we already have is we have metabolic dysfunction. And we see this with metabolic syndrome, with diabetes, obesity, fatty liver, etc. We see this atherogenic lipid profile in these states. And the question is always, why is the cholesterol elevated and contributing to the heart disease process? Is it just cholesterol we need to worry about, or is there something more going on that we need to correct? And I think obviously the answer is the latter, at least from my perspective. The next thing that we can see is during states of infection, another context where we see elevated cholesterol, we see the elevations of cytokines like tumor necrosis factor alpha and interleukin 6, and these can drive lipid production from the liver and raise the lipid profile. So this is another area where we see, okay, this is why we have elevated cholesterol levels. The next one we have is the lean mass hyperresponder hypothesis. And this model is showing us that the reason cholesterol is elevated is as a means to transport fatty acids to tissues when there isn't glucose available. The last one is hypothyroidism. So in a hypothyroid context, we actually see a decrease in the LDL receptor expression, and then the cells don't take up the cholesterol, the LDL cholesterol peripherally, and it starts to shift the lipid profile towards a more atherogenic profile, a profile more likely to cause cardiovascular disease, plaques, etc. So we have multiple hypotheses now, or multiple contexts or scenarios where we see the lipid profile becomes elevated, and while the cholesterol may be involved in cardiovascular disease, in all of these circumstances, the underlying elevation of the cholesterol is likely the culprit in the cardiovascular disease, and the cholesterol is playing a part in not necessarily specifically directly, more in like an indirect fashion, because it's being elevated as a byproduct of these different circumstances. Now, the lean mass hyper responder hypothesis is also extremely helpful because it brings to light the centrality of energy metabolism in understanding disease processes and physiology. And so this hypothesis is showing us how the body starts to repartition and how it starts to change its transport mechanisms for different components when you don't have adequate amount of carbohydrate, when you have to switch fuel substrate. So when you have to switch over to fats because adequate carbs aren't coming in, Dave Feldman, Nick Norwitz, and their team have actually shown us why this is happening and what actually goes on, and has laid out the mechanisms and delineated this context from other contexts. So this is extremely helpful. And it also, again, is showing the importance of energy metabolism in all of these different states. Now, the next piece that's extremely helpful with this hypothesis, or is useful with this hypothesis, is it tacitly challenges the lipid hypothesis. So the general lipid hypothesis is that cholesterol is the cause of heart disease, and that in general, we have to lower it at all costs, because the more LDL cholesterol we have inside our bloodstream, the more ApoB particles we have, the higher our risk of heart disease is. So lowering it is the best way to go about lowering our heart disease. And while lowering cholesterol would likely be the best way to lower heart disease, the mechanism by which we lower it would be important, because there's a culmination of factors that are required to actually develop or create heart disease, and that's oxidized cholesterol plus this immune response via macrophages. It's not just cholesterol by itself. So there's more factors that are triggering the cholesterol oxidation, that are triggering this immune response, and then eventually triggering the plaque formation beyond just the cholesterol by itself. And so this hypothesis here is saying, okay, here's a bunch of people that have really high LDL levels, and they have coronary artery calcium scores of 0. So they're not actually showing the development of plaques despite these high LDL levels. And that starts to make us question starts to bring into question, is the LDL the direct cause, or is the underlying pathology a cause? And if this is not pathology, is it then a problem? If this is a normal response to switching fuel sources from carb sources to fat sources, then is this a problem that the LDL is high? And if it's not, then that kind of brings into question the idea that LDL is just the problem that we need to focus on instead of these other underlying pieces. So I know the nuance here, the little shift, is relatively small, but the ramifications of that small nuance shift are very large and very important going forward. I also think the reason Dave Feldman, Nick Norwitz are getting all this backlash is because it challenges this lipid hypothesis, and it's challenged the entrenched dogma of cholesterol causes heart disease, take a statin. They're starting to bring things into perspective, say, yeah, it's not necessarily, or in this case, it kind of challenges the lipid hypothesis, because you're seeing that people are having cholesterol elevated without necessarily developing pathology. Okay, with that said, let's jump in and let's actually talk about what this hypothesis is. What are the steps? What are the mechanisms? What's going on in the body when somebody's on a very low carbohydrate diet and their LDL cholesterol is sky high? Okay, so in the lean mass hyperresponder state, it is a low carbohydrate state. So you have an individual who has a very low carbohydrate intake. Oftentimes, this individual is also quite lean. In some of the characteristics that they describe for the individual, they have a body fat percentage less than 20% for men, I think less than 23% for women. So they're on the leaner side overall. And the other thing is these individuals often are quite active. So they have a high activity level. So these are people who do not have metabolic dysfunction. They are lean, they are healthy, yet their LDL levels are sky high, their HDL levels are high, and their triglycerides are low. And these characteristics are important because they are very different than somebody who has an atherogenic dyslipodemia or a lipid profile that is showing or indicative of atherosclerosis. Those individuals would have high LDL, often low HDL, and often high triglycerides. So it's a different profile, and this is important to understand as we go in, and we'll talk about why it's different here. So the first quote that we have here that they share, they say, reduction in dietary carbohydrates and depletion of hepatic glycogen stores results in a greater demand for fat as a metabolic fuel to compensate for reduced glucose availability. So when you don't have adequate amounts of glucose, the body starts to use fat. Very simple. This is the first step in the hypothesis and the background of the context that I mentioned before. The next thing they say here is Decreased insulin, leptin, and other changes to the hormonal milieu result in increased hormone-sensitive lipase, mediated lipolysis in adipocytes, and greater secretion of non-esterified fatty acids into the bloodstreams. So less carbohydrates means less insulin, means less leptin signaling, and other hormones also shift, like increases in glucagon, adrenaline, etc. And this leads to an upregulation of an enzyme in the fat cells called hormone-sensitive lipase that breaks down the fats in the fat cells and releases them into the bloodstream. The reason why this is happening is because you don't have carbs available, so the cells still need a fuel source, so they're going to use fats. And where are they going to get this fats, especially under a fasting setup, is going to be from the fat tissue directly. So the body is releasing and breaking down fats when you don't have carbs and you're in a fasted state to provide the fatty acids to the cells to use. The next thing they say here is, in addition to heightened use by tissues in the periphery, there's a greater rate of uptake of non-esterified fatty acids by the liver. Under these conditions, there's a greater rate of synthesis of triglycerides from the increased fatty acid pool within hepatocytes. Increased rates of triglyceride synthesis in the liver leads to increased rates of hepatic assembly and secretion of triglyceride-rich, very low-density lipoproteins. So what happens? The fats are releasing a bunch of fatty acids. Muscles and tissues are taking up these fatty acids to use as a fuel source. And then the liver is also taking up these non-esterified fatty acids that are not formed together in triglycerides. And then the liver is packaging them in triglycerides. And then the triglycerides are being added to very low density lipoproteins and being exported out for transport. So the liver is taking up some of these fats and packaging them nicely and shooting them out to the tissues. Now, the next thing they say is in the increased very low density lipoprotein secretion rate in concert with greater lipoprotein lipase mediated turnover of very low density lipoproteins in peripheral tissues and a greater transfer of very low density lipoprotein surface components to HDL result in higher plasma levels of LDLs, low density lipoprotein cholesterol, and high density lipoprotein cholesterol. Okay, so what's happening? So we have all these VLDLs going out, these very low density lipoproteins. And when they go to the muscles or they go to the peripheral tissues, right, these tissues are using an enzyme called lipoprotein lipase. And it sounds exactly like what it does. It takes these lipoproteins and it takes the fats out of them. Lipase is lipo for fat, and then ACE is an enzyme that breaks something down. So lipase, so it's breaking down the fats from these lipoproteins. And so the reason why the tissues are doing that is to take in the fatty acids so that they can use them. Now, what happens when this occurs? Well, as the very low density lipoproteins start to get broken down, they actually start to leave LDL. LDL is what's left over, low density lipoprotein. These are lipoproteins that don't have all the triglycerides on them anymore because these cells have taken the triglycerides off. So essentially what happens is VLDL eventually becomes LDL as fats are taken off that VLDL. And the only difference between the two is the composition of them. So it's the same, largely the same components, but as the VLDL loses triglycerides and maybe there's some cholesterol esters and things like that, these other components get added. Now you get an LDL. So it's kind of like a transformation. It's like the VLDL is the caterpillar and the LDL becomes the butterfly after a bunch of changes, right? Very simple analogy, not exactly how it works in terms of the metamorphosis, but you guys get the idea. Now, the other thing that happens is HDL also gets some of the components from the VLDL. So the very low density lipoprotein has some surface components, cholesterol, lipoproteins, etc. And as it gets degraded, these excess pieces, these spare parts, get transferred to the HDL cholesterol. And so now you have more HDL cholesterol and you have more LDL cholesterol because you had a lot of VLDL and it just got broken down. And these two things are created as this VLDL is getting broken down. And again, very important to understand, where is the VLDL getting broken down? It's getting broken down at the tissues. The tissues are stealing all the triglycerides, the fats that are packaged off the VLDL, and using those fats as an energy source because there's no carbs. The carbs are gone, so we need to use something. Now, the next thing they say here is they say, focusing first on very low density lipoprotein metabolism, lipoprotein lipase liberates non-esterified fatty acids from triglycerides contained within the core of the very low density lipoproteins to supply local tissues with substrate for storage or oxidation. So the fat cells will store these fats and the muscle and cardiac cells will burn these fats, right? So this is what I was just saying, very low density lipoproteins. will go to the fat, the muscles, and the heart, and they will drop off the fatty acids from the triglycerides in these very low density lipoproteins. The fat tissue is storing this, and the muscle and heart are burning it. Something interesting here is you're on a low carb diet and you are still storing fat. So what's important to understand is it's not just about how much fat you are burning. It is also about how much fat you are storing in terms of losing body fat overall, and the reason I say is because some people say, oh, if I eat a high fat diet, since I'm burning fat, I can't gain weight. It's like if your rate of storage is higher than your rate of burn, you can indeed start to burn or start to gain fat tissue as you store more fats in the fat tissue than you actually release from the fat tissue. Now, the next thing is, they say here, depletion of the core triglyceride cargo of VLDL, very low density lipoprotein, requires a complementary remodeling and shrinking of the surface area of the lipoprotein. VLDL surface components, including apolipoproteins, free cholesterol, and phospholipids, are thus transferred to HDL, resulting in increased HDL-C and LDL-C, as well as elevated total HDL and LDL particle mass. So I'm going to share my screen here to show you guys an image of this occurring. So what we see here is we have this VLDL molecule, right? And the VLDL is the non-esterified fatty acids of fats are being taken off this LDL, right? You see the LDL is rich in this triglyceride. This VLDL is rich in the triglycerides, the TG. These are these little hairpin looking things in here. And then as these triglycerides are taken off, it eventually undergoes that metamorphosis and gets converted into LDL, which is smaller and less dense because it doesn't have all these triglycerides. And then also these surface components, phospholipids, cholesterol, and lipoproteins, go to create these HDLs or attach to these HDLs. So basically, the reason in the lean mass hyperresponder profile that we're seeing these really high LDL levels and these really high HDL levels is because the body is using the lipoproteins to transfer fats around. And in this process, as the fats are getting transferred around, you're getting a bunch of leftover components that are showing high on the lipid test, the lipid profile when you draw your blood. So basically the way you can think about this is VLDL is an Amazon truck filled with a bunch of packages that are fats. And the Amazon truck is delivering all these fats to these individual homes, these packages to the individual homes. And then now you have a bunch of Amazon trucks left over because you had all this transport going on. So you have a lot of circulating Amazon trucks in the form of LDL and HDL. So I'm going to stop sharing my screen here, get to the next quotes, and then we're going to walk through the whole model visually together. Now, the next quote that they say, an important prediction of the model is that the magnitude of change in triad components is positively associated with reliance on energy supplied by very low density lipoprotein triglycerides. Thus, as is shown in figure 1b, which we'll go through together, greater restriction of carbohydrate, lower adiposity, so lower relative adiposity, so the amount of body fat the individual has relative to their total size, and increased total energy expenditure related to lean mass, physical activity level, and other factors comprise independent variables that can be manipulated to test the model. So why is this so important? Why is it important that these people have less carbs, they have lower fat mass, and they have a higher energy expenditure? Why are these people seeing the biggest rise in cholesterol levels? The reason why is because they have less fat, they have less carbs coming in, so they need to rely more heavily on fatty acids, right? So that's the first thing. So you're not going to have all the carb transport going on because you have all the fat, you don't have the carbs coming in, so you have to rely on fat transport. Now, the next thing is the lower the body fat you have, the more you would technically have to rely on the liver transporting the fatty acids to these peripheral tissues because you don't have all these fatty stores releasing non-esterified fatty acids locally or around these different tissues. So now the liver has to be like, all right, we don't have all these depots, these little Amazon warehouses all over the place in the form of body stores. So now we have to actually start pumping out the fat from this central place, which is the liver, this central distribution depot in the form of these Amazon trucks, the very low density lipoproteins that provide everything to the tissues, to provide the fats to these tissues. So the leaner you are, the less fat you have, the more you have to rely on these transport mechanisms because you don't have the local depots of body fat. Now, the next thing is the increased energy expenditure. Why is this important? Well, if you have a high activity level and you have a very high lean mass, you have a more need for fuel. you have a much higher need for fuel. And so if you're really lean and you have a high activity level and you're restricting carbs, you're going to need a lot more fat to be transported to you through your Amazon truck so that you can use that for fuel, right? If your house is 5,000 square feet and you have to burn a lot of wood or a lot of fat to get this house warm on a regular basis, it's a very metabolically active house, then you're going to need a lot more shipments from Amazon to bring your fat packages or your wood packages to heat the house versus somebody who has maybe a store of wood in the back of the house and they're also only have a 2,000 square foot house that doesn't have 12-foot ceilings and whatever else to heat it. So when you have this individual who has a high energy demand, they're going to need more fats to float around to actually provide the fats to these tissues, or they're going to need more transport mechanisms to provide the fats to these tissues because their utilization of fats is going to be higher, which is why in leaner individuals who are more active and who have less carbohydrate intake, they have a higher LDL cholesterol and a higher HDL cholesterol. This is the hypothesis. And so this is not because of pathology. This is actually the body trying to compensate for the lack of local fuel depots and lack of carbohydrate and still maintain an adequate supply of cholesterol to or fatty acids to these tissues in this particular context, it's actually a really beautiful hypothesis because it's like in this context, these are the things that happen instead of the general medical model, which is just like, yeah, cholesterol is just bad across the board. We need to lower it. So I want to walk you through a graphic here to kind of wrap and summarize these components up so you can see exactly what I'm talking about. And so here's what we see. We see an individual who has a carbohydrate restricted diet and has low liver glycogen stores. Well, why is low liver glycogen important? Because the liver glycogen supports or supplies carbohydrate when you don't have adequate carbohydrate in. So you have to deplete your liver glycogen before this starts to occur, because if you have liver glycogen available, you'll start pushing it out and using it as a substrate, as a fuel source instead of the fats. So once your store of carbs is gone, now you're fully reliant on fats. Now, once the glycogen stores are depleted, you're on this carbohydrate restricted diet, your insulin levels, your leptin levels decrease, and then glucagon, adrenaline, and some of these other hormones start to increase, and then they will increase the signaling of a enzyme in the fat tissue called hormone-sensitive lipase. And so what hormone-sensitive lipase does is it releases fatty acids, non-esterified fatty acids. So what are non-esterified fatty acids? They're fats that are not bonded together in that triglyceride formation with kind of like a hairpin. So you have the glycerol backbone and 3 fatty acid tails. So they're just free fatty acids floating around. And so what happens? These free fatty acids are taken up by the muscle, by the heart, and also by the liver. And then what does the liver do? So, okay, let's talk about muscle and heart first. So the muscle and the heart will burn those fats. Maybe store them, but likely burn them in this context. So they're burning these fatty acids. They're using them as a fuel. That's how they're heating the house there. And the liver, what it does is it brings in the non-esterified fatty acids. Maybe it uses some of them, but it also then packages them in these nice Amazon trucks, the VLDL that we see here, these beige and green molecules. And so what winds up happening is then the liver sends out the VLDL to the peripheral circulation, to the muscle, to the heart, and to the fat tissue. And then basically the VLDL has the triglycerides and the fatty acids unloaded from it. And as those triglycerides and fatty acids are unloaded from the VLDL, you get LDL and you get HDL increase. These are kind of the remnant components that are left after VLDL is degraded. Now at the tissues, how are the tissues taking up these fatty acids? They're taking it up via, you see here, lipoprotein lipase mediated VLDL turnover. So the cells are expressing kind of like it's like a docking station. It's like a guy there at the house who gets the package for you, or you can think of it like your mailbox. So you have this little mailbox there that picks up the fats. So the fats are put into the mailbox, and then the cell, the muscle can use them, the fat tissue can store them, or the heart can use them. So you basically have this circumstance where you're circulating a lot of free fatty acids, and then the liver is packaging these fatty acids into transport. And then once the fats are used at these different tissues, we have a bunch of these transport trucks, these LDL and HDL left over. And this is why we're seeing those high levels of these lipoproteins in the lean mass hyperresponder phenotype or profile. Now on the bottom here, what we see, this is just explaining the low carb So the lower your carbohydrate intake, the lower your fat tissue, the higher energy expenditure means that you have more, they say lipoprotein lipase mediated VLDL turnover, meaning you have more packaging of fats into VLDL, shipping out that VLDL to the tissues, and then the tissues using lipoprotein lipase, that nice little mailbox, to collect the fats and then use them. And so that creates more HDL and LDL. And that's the profile you see here. The lean mass hyperresponder has a high HDL-C, a high LDL-C, and low triglyceride counts. So this is why we're seeing that. These guys have actually laid out why we are seeing this occur and gone through all the mechanisms, which is very nice to see, especially with all the backlash that they get from the mainstream. They actually used a bunch of research and studies to lay this out and describe the mechanisms, and it makes a lot of sense when you actually go through it. Now, in the next section, what I want to talk about is the idea that energy metabolism is the driver here. This is absolutely key in this circumstance. And we'll see why this is key in just a bit when we start to compare the atherogenic lipid profile and the lean mass hyperresponder lipid profile, because it actually becomes really interesting and important there to describe why are we seeing people have an atherogenic lipid profile in these metabolically impaired states like diabetes, obesity, impaired glucose tolerance, fatty liver, etc. And so the nice thing about this is it highlights that the lipoproteins, again, are elevated here, mainly to transport fatty acids to the tissues, because fatty acid oxidation is upregulated, and the fatty acid oxidation is upregulated when you don't have adequate carbs coming in, liver glycogen is depleted, and you shift the hormones, you lower insulin signaling, you lower leptin, you raise glucagon, you raise adrenaline, possibly cortisol as well. So we're seeing this whole series of shifting play out very nicely, where when you have carbs, you shift insulin and it lowers this process. And when you don't have carbs, you start to raise fatty acids, insulin drops, and these other adaptive hormones come in. And this aligns actually perfectly with the bioenergetic perspective as far as what's going on in the different states between fat oxidation and carb oxidation. Okay, so let's get into some specific components of this hypothesis. So what I want to do is I want to explain the specific differences between the lean mass hyperresponders and the atherogenic dyslipidemia. I'm going to use their paper here because they describe it. They describe the differences in this paper. And I want to specifically focus on lipoprotein lipase activity because I think this is extremely important here. The next thing is I want to highlight, after going through that, the importance of energetic failure at the mitochondrial level as the driver of atherogenic dyslipidemia. So it's not carb intake, it's not necessarily fat intake, it's mitochondrial dysfunction. And so we're going to see in some studies, I'm going to show you that fat metabolism is impaired in obesity. Obese individuals also have issues with carb metabolism. The mechanism, we'll talk about mechanisms of mitochondrial disruption in obesity and likely diabetes. So what is actually causing this disruption? What are we seeing in the mitochondria? And then what we'll talk about is that the energy failure at the mitochondria is leading to a backlog of all substrate, including lipoproteins, fatty acids, and glucose in the blood, in the serum, because of downregulated lipoprotein lipase activity, because of metabolic dysfunction at the cell. And then basically the backup from there is what's driving this elevated lipid profile. So again, the central piece is still energy metabolism. With the lean mass hyperresponders, you don't have carbs, so you're shifting the fats, and you have all these mechanisms to do that. But then in atherogenic dyslipidemia, the reason that you're seeing this backlog of substrate inside the blood is because there's actually a failure at the metabolism, so the fuel can't get in and be used. So it just piles back up in the blood, and I want to show this. Okay, so let's talk about the difference between atherogenic dyslipidemia and lean mass hyperresponders. So they actually describe the difference in the paper here, and I want to go through what they describe. So now they're going to describe in atherogenic dyslipidemia, why do we see low HDL cholesterol, whereas in lean mass hyperresponders, we see high HDL cholesterol? We already talked about why we see high in lean mass hyperresponders. So let's talk about why we're seeing it low in dyslipidemia, which has high LDL. So they start here and they say cholesterol ester transfer protein facilitates the exchange of core lipids, cholesterol esters for triglycerides between lipoproteins. Specifically, cholesterol ester transfer protein is primarily bound to HDL and facilitates the transfer of cholesterol esters from ApoA1 containing HDL to triglyceride-rich lipoproteins and LDL in exchange for triglycerides from these ApoB containing particles. So essentially what happens is HDL is trading cholesterol esters to triglyceride-rich lipoproteins and LDL under atherogenic dyslipidemia. And so the HDL starts to get enriched in triglycerides, and then the triglyceride-rich lipoproteins and LDL start to get enriched in cholesterol esters and lose their triglycerides to the HDL. The next thing they say is that cholesterol ester transfer protein activity is largely driven by the availability of triglyceride-rich lipoproteins. Similarly, simply stated, higher levels of triglycerides in ApoB-containing particles like very low-density lipoprotein and low-density lipoprotein drives increased cholesterol ester transfer protein activity by increasing availability of triglyceride substrates. Conversely, in the context of low levels of triglycerides in ApoB-containing particles, there's little demand and little driving force for cholesterol ester transfer protein activity. So basically, if you have a high amount of triglycerides floating around in VLDL and LDL, cholesterol ester transfer protein starts to increase the removal of the triglycerides from these specific lipoproteins to HDL. And so it's a way to kind of unload some of these trucks because they're driving around and they have nowhere to drop off the fats. There's no packages to drop off. So you start to have HDLs like, all right, this is like it's like a relief for these Amazon drivers. The trucks are filled with packages. They can't drop them off at the tissues. Again, this is atherogenic dyslipidemia. So you have metabolic dysfunction. So the tissues are not taking up the fats, the triglycerides. So HDL is kind of like the relief service that comes in and is like, all right, Amazon trucks, we're going to take off some of the packages to take off some of the load to you. And then the HDL brings it back to the liver. So we're going to see this in just a second here. So they say in atherogenic dyslipidemia, insufficient, very low density lipoprotein turnover relative to secretion, likely in part due to ApoC3 mediated inhibition of lipoprotein lipase, causes triglyceride-rich lipoprotein levels to rise and increases triglyceride-rich triglycerides in favor of increased cholesterol ester transfer protein activity. As a result, there are higher levels of cholesterol ester transport protein mediated exchange, and HDL particles become relatively triglyceride-rich and cholesterol ester poor. So this is a high triglyceride to cholesterol ester ratio corresponding to reduced HDL-C levels. They say here, so how is these HDL being released? I'm going to bring it all together and translate this, I promise. They say triglyceride-rich HDLs are also prone to hepatic lipase-mediated lipolysis. Activity of hepatic lipase is also elevated in atherogenic dyslipidemia, and ultimately accelerated HDL clearance by the liver and kidneys, further depleting HDL. So what happens? The HDL cholesterol, the HDL lipoprotein has cholesterol esters. When you have all these triglyceride-rich lipoproteins, VLDL, LDL, they're filled with the triglycerides, they're floating around, and they can't drop off these fats to the tissues because lipoprotein lipase is not taking them up. What winds up happening is HDL starts to take off the triglycerides, take off the packages. And then when the HDL takes off the packages, it brings it to the liver, and then the liver starts to break down the HDL and take the fats off the HDL. So it's pulling the HDL out of circulation. And now you're seeing less HDL floating around in atherogenic dyslipidemia because it's trying to clear off all these unused fats on the VLDL and LDL because the tissues are not taking up those fats because lipoprotein lipase is shut down. Now they're saying here that lipoprotein lipase is shut down because of ApoC3. And it's like, sure, that's great, but why is ApoC3 elevated? And I think that the reason you're seeing it shut down is because there's metabolic dysfunction directly at the cell, and that this is basically the cells can't take up more fatty acids. They can't take up more triglycerides. They also, we see with insulin resistance, which is what you see in this atherogenic dyslipidemic state, is they can't take up carbohydrate very well either. And again, this is because the cells are metabolically impaired. And we're going to see this in just a sec, I promise. So the last quote they say here, they say, in brief, inefficient lipoprotein lipase mediated very low density lipoprotein turnover and increased very low density lipoprotein levels marked by elevated serum triglycerides drive higher rates of cholesterol ester transfer protein mediated transfer of triglycerides to HDL and consequently depletion of HDL-C and accelerated HDL catabolism. So this is basically what I just said. When the VLDL is unable to unload its triglycerides, then the HDL starts to trade the cholesterol esters it's holding to the VLDL and then take the triglycerides. So that depletes HDL cholesterol. So the HDL molecules become depleted of cholesterol. So you see a lowering of HDL-C. Then the next thing that happens is with these HDL particles loaded with triglycerides, they go to the liver, and then the liver starts to catabolize them or to break them down to presumably to get rid of the lipoproteins, kind of get some of this stuff out of circulation. So it's this like bringing this, it's basically this intricate transport network to bring the packages back to the liver because the cells at the peripheral cells cannot take them up. So actually, I'm going to show you this in a graphic here. I'm going to share my screen. So what we're seeing here, we see the atherogenic dyslipidemic profile. Okay, so what we're seeing here is the atherogenic dyslipidemic profile. So we see an individual, they're overweight because they likely have metabolic dysfunction. Their triglycerides are elevated, their HDL levels are low, and then they have an increase of small, dense LDL. So we'll talk about that in a second. I didn't get to that specifically here. It'll be in the next section. Then what we see is the LPL lipoprotein lipase mediated triglyceride-rich turnover. So the breakdown of the very low density lipoproteins, these Amazon trucks, where they put the packages in lipoprotein lipase, which is the mailbox, that's blocked. The house is filled with packages, and the garbage servants hasn't come, and they're not using the packages. The house is not burning the wood. The house is stuffed with wood, so it can't take new wood to produce more energy. So what winds up happening is the Amazon trucks that are transporting all this wood, this fat, the fuel, they're just floating around. They're moving around. There's a lot of them now, and they're not empty now. They're full. They're filled with these triglycerides. And so what winds up happening is cholesterol ester transport. So basically, this is a guy who comes and takes the packages off of these triglyceride-rich trucks and puts them on these relief trucks, these HDL trucks, to bring them back to the distribution warehouse to deliver. He starts to increase his work, and he starts to say, okay, we're going to take some of these fats off of you guys. We're going to give them to the support crew, and the support crew is going to give you guys, I guess, IOUs in the form of cholesterol esters to give to the triglyceride-rich lipoproteins. Now, what then happens is the HDL is then decreased because they bring the fats back to the liver. They've lost their cholesterol, and so the lowering of HDL-C, the lowering of the cholesterol in HDL is indicative of this problem because it had to transfer the cholesterol esters to these in exchange for the triglycerides to these triglycerides-rich lipoproteins. So it's basically a sign. It's a signal to say, hey, we have a bunch of triglyceride-rich lipoproteins floating around and they're not being taken up in the cell. So it's a symbol or signal of this metabolic dysfunction at the cell indirectly. And then what winds up happening is the HDL goes to the liver, and the liver breaks down the HDL, takes out these extra triglycerides, and then decreases the overall HDL pool. So that's what we're seeing here. And this is why HDL is low in atherogenic dyslipidemia, whereas in the normal, the lean mass hyperresponder circumstance, HDL is high and HDL-C is high because the VLDL is actually being taken up. The fats are being taken off of it at the peripheral tissues. The tissues are using the triglycerides stored there, and then the remnants are going to actually make more HDL. So you don't have a bunch of HDL that's actually loaded with triglycerides in the lean mass hyperresponder profile because the triglycerides are being used, the fats are being used. But in this state, because you have metabolic dysfunction at the cell, the fats are not being used, and therefore they're floating around in HDL to try to relieve the load from the triglyceride-rich lipoproteins, the very low-density lipoproteins. And we're going to talk about why we see small, dense LDL in these states and not necessarily a lot of normal LDL or medium-sized, larger-sized, buoyant LDL like what we would see in the lean mass hyperresponder profile. So in the atherogenic dyslipidemic profile, we see this small, dense LDL, which has been highly associated with cardiovascular disease, where you don't necessarily see that inside the lean mass hyperresponders profile. So let's dig in and talk about why this occurs. So what they start here, they say, well, HDL particles serve as a preferential cholesterol ester donor, or essentially they are the triglyceride acceptor for cholesterol ester transport protein mediated exchange. Triglyceride-rich lipoproteins and their remnants that are elevated in atherogenic dyslipidemia also undergo cholesterol ester transfer protein mediated exchange, in which they are the cholesterol ester acceptor, triglyceride donor with other ApoB particles, including LDL, resulting in triglyceride-enriched LDL. So what they're saying here is LDL also will take up some of the triglycerides from the triglyceride-rich lipoproteins, like very low-density lipoproteins. This is occurring via the enzyme cholesterol ester transfer protein, and this leads to triglyceride-enriched LDL. Again, this is just showing a symptom of the problem. the VLDL cannot unload the fatty acids at the tissue, presumably because of metabolic dysfunction, because you're usually seeing this in states of metabolic dysfunction. And so then the fats have to get transported to LDL and also the HDL. All right, so it's basically like, well, what are we going to do with all these fats, the VLDL is saying? And an HDL and LDL are like, all right, man, we got you. We'll help you out. We'll take some of these fats off. And then what they will move these fats to go somewhere else. And basically what we're going to see is they go to the liver and they get to catabolize, they get broken down. So what they say here is they say triglyceride-enriched LDLs are likewise prone to hepatic lipase-mediated lipolysis as with triglyceride-rich HDL, resulting in small, dense LDL particles and the pattern B phenotype. So what happens is the LDL and the HDL both go to the liver, they drop off the triglycerides, and then you basically, what's left over after these LDL drop off all their triglycerides is small, dense LDL particles. And this is the small, dense LDL particles, as I mentioned, are associated the most with cardiovascular disease, not the larger, more buoyant LDL particles. And essentially, this is called the pattern B versus the pattern A phenotype. And the pattern B is strongly associated with cardiovascular disease. And again, the problem here, I think this is a signal, a symptom of metabolic dysfunction. And it's the metabolic dysfunction is driving this process, because essentially what you're seeing is, why are we getting small, dense LDL? Because VLDL can't get rid of the fats, the triglycerides at the peripheral tissues, because they're dealing with metabolic dysfunction. And then that's leading to the LDL and HDL taking up all of the triglycerides to try to unload some of these fats floating around on the VLDL in the blood. Now, what they say here, they say, in summary, the extent of decreased lipoprotein lipase-mediated triglyceride-rich turnover rate and increased levels of triglyceride substrate and ApoB-containing particles can drive enhanced cholesterol ester transfer protein mediated transfer of triglycerides from triglyceride-rich lipoproteins to HDL and LDL, leading to depletion of HDL as well as a preponderance of small, dense LDL that defines atherogenic dyslipidemia. So basically what they're showing is that because triglyceride-rich lipoproteins like VLDL are not unloading the triglycerides at the peripheral tissues via lipoprotein lipase, you're getting this increased profile of triglyceride-enriched HDL, which is cholesterol poor, and then you're getting triglyceride-enriched LDL that eventually becomes catabolized by the liver that produces small, dense LDL. So these are the mechanisms to show us why somebody who has atherogenic dyslipidemia actually has a low LDL level and has high LDL that's in the form of small, dense lipoproteins and also a lot of floating triglycerides. The reason the triglycerides are high and floating around, we didn't specifically mention it here or go through the mechanisms as in depth in this paper, is because they're not being uptaken. So you just have a lot of triglycerides floating around in the state. And again, primary thing you understand is the metabolic dysfunction is happening at the cell. So the cell is not taking up this fuel. Fats and carbs are fuel. In the metabolic dysfunction state, diabetes, obesity, impaired glucose tolerance, fatty liver, the cells are unable to use the fuel appropriately. So you have a bunch of fats floating around and you have a bunch of glucose floating around. And then because the glucose is floating around, it can't take up the insulin or the glucose. And that leads to hyperinsulinemia, high free fatty acids, and high glucose. And again, the bottleneck is the energy metabolism at the cell. So that needs to be corrected. And this also predisposes towards cardiovascular disease because of the change in the lipid profile here. And also it likely contributes because it creates a lot of reactive oxygen species. Because when you have this metabolic dysfunction, you start to produce large amounts of ROS. And then the ROS can actually start to oxidize the lipoproteins, and then oxidized cholesterol is one of the primary drivers for cardiovascular disease. Normal cholesterol is not necessarily causing the issue, but oxidized cholesterol is. And this lean mass hyperresponders model is beautiful to help us see that or to give us some indication further that metabolic dysfunction is driving the problem. Now, what I want to do is I want to talk about energy failure as the key. There's some quotes here from the lean mass hyperresponders group where they're trying to show in obesity that a shift towards fat-based metabolism is impaired. And I don't think it's just a shift towards fat-based metabolism. I think it's a shift of all metabolic substrate is impaired in obesity. And we're going to talk about the mechanisms of that, but I want to go through some of the studies here that they discussed. So what they say here in this first study is they say as early as 1977, Goschke observed that a 6-day fast increased plasma non-esterified fatty acids and ketones to a greater extent in subjects who are lean versus those with obesity. Plasma non-esterified fatty acids and ketones in the lean participants were 22% and 30% higher, respectively, as compared to levels in those with obesity after 6 days of fasting. A particularly notable finding, considering that plasma non-esterified fatty acids tend to be higher among subjects with obesity at baseline or on a diet including carbohydrates. So what's happening here? Lean individuals who go on a fast have higher amounts of ketones and fatty acids generated than or released into serum than the obese individuals. So why is this important? Well, we know obese individuals have problems with metabolism. That's arguably why they're actually storing all of this body fat. And so my argument here is they probably don't need to release as much fatty acids into their circulation because they don't need as much fuel as somebody who's very lean, has a high and who has a higher metabolic rate. So they can get by on much less fuel because their metabolism is directly impaired. Obviously, this isn't a good thing. This isn't saying that their metabolism is more efficient. Obese individuals have a variety of problems. For example, usually lower energy, fatigue, hormonal stuff going on, which is not to say that they're functioning better on less fuel. It's they're functioning worse on less fuel and less metabolic energy. They're using less fuel because they are actually functioning worse because metabolism is worse. The other thing here is the obese individuals are known to have a higher amount of plasma non-esterified fatty acids at rest and even on a carbohydrate-based diet than normal subjects. And so basically what this says to me is maybe they also release less because they already have a bunch of free fatty acids floating around in the bloodstream that aren't being taken up, again, because the obese individual has metabolic dysfunction specifically at the mitochondria. So they're not having the flow of fuel into the mitochondria and then the production of energy. There's a block in the mitochondria that's impairing that process from occurring. The next study they show here, it says, furthermore, Wingegarden et al. Demonstrated that the shift from glucose to lipid oxidation is attenuated by obesity during a fast. In this study, over a 48-hour fast, there was a 214% increase in lipid oxidation in lean subjects as measured by indirect calorimetry as compared to a 76% increase in those with obesity, with an accompanying decrease in resting energy expenditure observed in those with obesity only. So again, this is showing more evidence that the obese individual has metabolic impairment at the mitochondria, and it is driving this decreased lipid peroxidation and also decreased glucose oxidation. So it's not even that they're having an issue shifting from carb oxidation to fat oxidation. They're just having a problem with oxidation, period, whether it's carbs or whether it's fats. And then the question is why. The question of the year, the question of the century is why are these individuals actually having metabolic dysfunction? What is causing the issue on the mitochondria? I'm going to talk about some of the mechanisms in the next slide here, or in the next section here, but I wanted to just point this out. So basically, when obese individuals fast, they actually lowered their metabolic rate here. So their metabolism decreased even further. So they just adaptively downregulated their metabolism instead of increasing the oxidation of the substrate. Whereas in lean individuals, they started increasing fatty acid oxidation again because they don't have the carbohydrate coming in. So in obese individuals, it's arguably worse because you're lowering the metabolism even further, and it's already lowered to a large extent, which is what we saw in the previous study. And we'll talk about this in the next set of quotes. Let's see what's going on when we look at a diabetic, an obese individual, and a lean, healthy person in terms of their mitochondrial function. So I have a study here that I want to go through that'll show us that the dysfunction is in the mitochondria. And we're going to look at these three different types of people and look at the function of their cellular energy metabolism inside the mitochondria versus in glycolysis, which is the Krebs cycle is not working in the diabetic and the obese individual as well as it is in the lean individual. The obese individual and the diabetic are forced to and stuck with glycolysis. So we have the paper here, and they say in this paper, they say, the insulin resistance of skeletal muscle in glucose-tolerant obese individuals is associated with reduced activity of oxidative enzymes and a disproportionate increase in activity of glycolytic enzymes. Activity for glycolytic enzymes, phosphofructose kinase, glycerolaldehyde phosphate dehydrogenase, and hexokinase was highest in subjects with type 2 diabetes, following the order of type 2 diabetes being the worst, obese individuals being the second worst, and lean individuals being the best, whereas maximum velocity for oxidative enzymes in the form of citrate synthase and cytochrome C oxidase was lowest in subjects with type 2 diabetes. So essentially what you're seeing is people who are stuck with diabetes or obesity are stuck in this type of metabolic state have their glycolytic enzymes upregulated. So these are the enzymes that take carbohydrates and turn them, I mean, usually it'd be turning them into pyruvate, but in this circumstance, it's likely going to be towards lactate because the pyruvate cannot be used to go into the Krebs cycle because the citrate synthase and cytochrome C oxidase, so citrate synthase is in the Krebs cycle and cytochrome C oxidase is in the electron transport chain. Both of those activities are much lower than you see in the lean individuals. And so what winds up happening is their ability to take carbohydrate, convert it to pyruvate through glycolysis, and then take that pyruvate and turn that into ATP through the Krebs cycle and through the electron transport chain is drastically impaired compared to normal people. So they just run it through glycolysis. They just turn it to lactate. And it's basically this you're seeing here is energetic failure, mitochondrial failure. So there's a problem in the mitochondria, presumably, that's leading to this occurring, right? So the next thing they say is the ratio between glycolytic and oxidative enzyme activities within skeletal muscle correlated negatively with insulin sensitivity. So essentially, the higher glycolytic enzyme activity that you had and the lower oxidative enzyme activity you had, the more insulin resistant you were. Whereas the higher oxidative enzyme activity you had and the lower glycolytic activity you had, the less insulin resistant you were, or the more insulin sensitive you were. So basically, when the mitochondria is working, when the oxidative enzymes are working, and the glucose is able to move through the mitochondria from glycolysis, it gets converted to pyruvate, get into the Krebs cycle, and then go to the electron transport chain, and then it's producing the 32 or 36, 38 ATP, and you have the carbon dioxide in the water. Then it's like now you're really insulin sensitive because the fuel is used appropriately. Whereas if you have mitochondrial dysfunction and the fuel is not used appropriately, then what you start to see is insulin resistance, because now the cell is saying, well, great insulin, thank you for dropping off this fuel, but we can't actually use it right now because the furnace isn't working. So we're just going to stay cold. We're just not going to have this metabolic activity that we need. Now, the last thing they say here is they say, in summary, an imbalance between glycolytic and oxidative enzyme capacities is present in insulin and a non-insulin dependent diabetes subjects and is more severe than in obese or lean glucose tolerant subjects. The altered ratio between glycolytic and oxidative enzyme activities found in skeletal muscle of individuals with type 2 diabetes suggests that a dysregulation between mitochondrial oxidative capacity and capacity for glycolysis is an important component of the expression of insulin resistance. So in these states, the obese individual and the type 2 diabetic individual have a hard time not only using fatty acids, as we saw with the research that Dave Feldman and Nick Norowitz paper and team have showed us, they also have a problem with glucose utilization and being insulin resistant. And this is characterized by actually having mitochondrial failure and being forced to run through glycolysis. So this highlights mitochondrial failure, I think, as the problem. Now, the question is, and I'm going to share some graphics here, what is actually going on in the mitochondria? Why are we seeing this failure? And so what they say here is they say cytokines, tumor necrosis factor alpha, and interleukin 1 activate inducible nitric oxide synthase and nitric oxide synthesis. Mitochondrial aconitase is inhibited and the citric acid cycle is disturbed, resulting in decreased ATP production and increased mitochondrial citrate levels. Citrate is transported to the cytosol and activates acetyl-CoA carboxylase and fatty acid synthesis. Acetyl-CoA carboxylase and malonyl-CoA inhibit carnitine and palmitoyl transferase 1 and beta oxidation. Obesity can amplify cytokine expression. So what are these guys even saying? That was like a lot of jargon, but what exactly is going on here? Okay, so what we see, essentially what's going on is tumor necrosis factor alpha and interleukin 1. So inflammatory cytokines, inflammatory mediators are upregulating inducible nitric oxide synthase. This is very different than endothelial-derived nitric oxide synthase, and we're getting a production of nitric oxide and also likely reactive oxygen species inside the electron transport chain. They don't describe that here. And so the nitric oxide and ROS can directly block aconitase inside the citric acid cycle in the mitochondria. Now, why is this important? Well, aconitase is one of the key enzymes that's involved in the Krebs cycle and basically taking carbohydrates and fats through beta oxidation and turning them into energy. So if aconitase is blocked, this step in the metabolic pathway is blocked, nothing flows through. The only thing that can happen is you can start to shift amino acids down around alpha ketoglutarate. And so basically what's going on is you have this block in the mitochondria. Now what happens? When aconitase is blocked, When carbs come in, they get converted to acetyl-CoA. And when fats come in, it all gets converted to acetyl-CoA, and then you get citrate. But since citrate cannot move through a aconitase towards isocitrate, but what winds up happening is you get a buildup of citrate in the mitochondria that backs up outside the intermitochondrial space, and you wind up getting a buildup of malonyl-CoA. So what happens when you get a buildup of malonyl-CoA? Malonyl-CoA is the main signal in the mitochondria to block carnitine palmitoyl transferase 1. So with the buildup of malonyl-CoA, you now block fatty acid oxidation. And with the glucose oxidation, since you can't actually flow the pyruvate anymore to acetyl-CoA through citrate because you have this backlog, the pyruvate just starts getting shifted towards glycolysis. And so now this is what you're seeing in diabetes and obesity. You're seeing an inability to oxidize fatty acids, likely through some of these mechanisms, block at aconitase through ROS and inflammatory signaling. And then also you're getting a shifting of carbohydrate to run through glycolysis because it can't move through the electron transport chain anymore. And so now you're seeing a complete block at the mitochondria, and this can help us to explain what's going on with the other areas of diabetes and obesity and why we're seeing these shifts. Now, the next thing, so basically the overarching model that they show here is you have some type of inflammatory event, maybe inflammatory or oxidative stress. This elevates these cytokines, tumor necrosis factor alpha, interleukin 1. They disturb the citric acid cycle, the Krebs cycle, by blocking aconitase through nitric oxide signaling and basically backlogging all of the Krebs cycle. Now you have decreased ATP synthesis from the electron transport chain because you're not producing NADH and FADH appropriately to actually carry electrons into the electron transport chain. You have increased fatty acid synthesis because the fats can't be used now because beta oxidation is blocked by the buildup of citrate and the overloading of malonyl-CoA blocking carnitine palmitoyl transferase 1. And then you're blocking the fatty acid oxidation. So fats are being synthesized. This fuel is being shuttled into fats. Carbs are being run through glycolysis or being converted to fats through acetyl-CoA carboxylase and turning into malonyl-CoA and then fatty acid synthase. And then now you have an energy deficit with a buildup and shuttling of things to fats, and the cell is stuck running glycolysis. Now this leads to diabetes and obesity phenotype where you have increased appetite and increased food intake. This is because of actual low cellular energy despite adequate fuel. And this is why we always talk about the importance of understanding the conversion of fuel to actual energy through all these processes. And you also see restricted energy expenditure. So people who have obesity and diabetes are often fatigued and tired, and then they're not able to lose weight effectively. And how could they lose weight if they're not able to actually take fuel and convert it to energy? They're just turning everything into fuel. And a lot of people that I work with will experience this and say, hey, like I'm doing everything and I cannot lose weight. And a lot of times they are, and they are not losing weight, or they need severe deficits to lose weight and then they feel terrible. And again, the problem is not necessarily that they're gluttons. Maybe there's a point in time they were eating a bunch of crappy food that was causing a variety of problems that led to endotoxemia. They loaded their mitochondria up on polyunsaturated fatty acids, and now their mitochondria aren't working because of those things. But now when they try to fix it, it's like they have these huge blocks to correct. And so this is what we're seeing in obesity. We're actually seeing obesity, diabetes, et cetera, this metabolic dysfunction at the cell. And the reason I'm showing you this is because I think that this is what leads to a backup in the lipid profile is the fats and carbs can't flow through. So you're seeing increased blood glucose concentrations. You're seeing increased insulin because insulin gets degraded at the cell when the cell takes it up with the carbohydrate. And then you're also seeing increased fatty acids floating around and increased lipoproteins, LDL, and because you can't transport the fats. So you're getting high VLDL, high LDL, high insulin, high free fatty acids, high blood glucose. And basically, it's like, why are we seeing all this? This stuff should not happen. When you don't have carbs, you burn fats. When you have carbs, you don't burn fats, right? You burn carbs. So there should be this switch. But in these states, because of metabolic dysfunction, you're not seeing the switch anymore. And you're seeing that back up into this transport network, which is the lipid profile in the bloodstream. And something important to understand is that the bloodstream is supposed to be a transport highway. So you're seeing jams in the highway because the delivery trucks, whatever else, are not able to get their packages through. So they're just kind of circulating around and creating traffic. And this is the general idea, I think, of what's going on and what explains that. And that energy deficit is actually the central piece here. So to wrap this video up, what I want to do really quick is I want to say that while the lean mass hyperresponder stuff, the hypothesis, the mechanisms, the work that these guys are doing is great, I really respect them. I think they're doing a great job. I think their understanding of nuance is top notch. And I really like the ideas and content and things that they're putting out. I think that it's awesome. But I wanted to highlight with this video the importance of energy metabolism in this problem and and take their hypothesis a step further. That's kind of what I want to do. I want to add to the discussion of what they're saying instead of just like rehash it. And so as I was reading their papers to make this video, I started to see this relationship play out. And I started to say, oh, maybe we can see how the energy metabolism is a major problem here. So I wanted to highlight this in this video and show that the lean mass hyperresponders is actually congruent with the bioenergetic perspective in terms of understanding the switch between carbs and fats. And then also it's helpful for us to understand why cholesterol is elevated and highlighting energetic dysfunction as the key point in diabetes and in obesity and impaired glucose tolerance in these metabolic syndrome states. And that's leading to changes in the atherogenic lipid profile and also an inability to not only use carbs, but also an inability to use fats. And I think this kind of rectifies paradoxes and brings everything together and makes this less of a carbs versus fat problem and makes this more of a energy failure is the central problem inside these disease processes. And the question is, how do we fix this energy failure? What is directly causing this energy failure? And so I've provided some mechanisms that describe this energetic failure. I think there could be more. I think polyunsaturated fatty acids are a big piece in this, especially as they get incorporated into the mitochondria. But I think the mitochondria are central to these disease process. The literature is showing this more and more. And I think we need to focus there and kind of get out of the dietary wars and start to understand like, why is this occurring? And what are the mechanisms and things that we need to do to correct this so that we're able to take carbs and fats, whatever the fuel source we're using, and actually convert it appropriately into energy. Now, with this video, I hope you guys like it. If you want to see more content like this or you have specific content that you want me to cover, please drop a note in the comments and please give this video a thumbs up and please subscribe. And I'll catch you in the next video for some more super in-depth dives into different hypotheses and physiologic mechanisms.